Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 19th, 2026, just 2 days ago. It demonstrates that we can achieve robust cooperation between self-interested agents without complex meta-learning rules or hard-coded assumptions. Instead, the authors show that training sequence models against a diverse set of opponents naturally induces cooperative behavior through in-context learning. The paper is titled Multi-Agent Cooperation Through In-Context Co-Player Inference. And as we'll see later, the results suggest that standard decentralized learning is powerful enough to resolve difficult social dilemmas. Figure 1 backs this up by tracking training progress for two algorithms, predictive policy improvement on the left and advantage actor-critic on the right. In both cases, the solid red lines represent the proposed mixed pool training, where the cooperation rate climbs significantly. By contrast, look at the dotted and dashed lines hovering near zero at the bottom. These represent agents trained without diverse opponents or with explicit IDs, and they fail to cooperate entirely, proving that uncertainty is what actually drives the learning process. While the previous results confirmed cooperation, Figure 2 explains the mechanism through 3 evolutionary steps. First, the top row shows that training against diverse opponents creates an agent capable of, in-context, best response, adapting its strategy instantly, as seen in Panel B. Next, Step 2 in the middle row reveals that this adaptability makes the agent vulnerable to extortion by a savvy opponent. However, the bottom row shows the resolution. When two such extortionists meet, their mutual pressure forces a change. As Panel E illustrates, they effectively shape each other into cooperating, driving the cooperation rate to nearly 100%. So, to ground those dynamics, Table 1 presents the specific payoff matrix for the iterated prisoner's dilemma used here. It is a standard setup where mutual cooperation grants 1 point to each agent. However, if one agent defects while the other cooperates, the defector gains 2 points and the cooperator loses 1. This structure creates the fundamental tension, because while mutual defection yields 0, the temptation to defect for a higher immediate reward always exists. Alright, moving from the game rules to the agent configuration, Table 2 details the specific hyperparameters used for the advantage actor-critic algorithm. The columns track the settings across the 4 evolutionary steps we discussed earlier. For instance, notice that the batch size doubles from 2048 in Step 1 to 4096 by Step 3, while the learning rate decreases significantly. These adjustments help stabilize training as the agents face increasingly complex opponent dynamics. Well, having set those parameters, Figure 3 zooms in on behavior within a single episode early in the training process. Panel A on the left tracks the PPI agents. Focus on the solid red curve in the cooperation rate plot. Notice how it starts near 0, but climbs steadily as the rounds progress. This reveals that learners initially attempt to extort each other, but the resulting pressure quickly drives them toward cooperation. In contrast, the pink line in the average reward plot shows the agent correctly identifying and exploiting a naive, always cooperate opponent. While Figure 3 analyzed the predictive policy model, Figure 4 breaks down the advantage actor-critic algorithm across 3 evolutionary steps. The top row shows the agent learning to best respond against diverse opponents, with Panel B confirming it adapts to strategies like tit for tat. Next, the middle row demonstrates how a second agent learns to extort this adaptive learner, driving rewards above 1 in Panel Circa. Finally, the bottom row reveals that when two extortionists meet, they initially cooperate, although Panel E warns that this stability can degrade into defection over time. Wrapping up, 2 takeaways stand out. Complex meta-learning rules are unnecessary for cooperation, and diversity is key. Simply training sequence models against varied opponents naturally induces cooperative behavior through in-context learning. This suggests that as AI agents become more capable, they might naturally resolve social dilemmas without heavy engineering. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.